Hello again. I'm back with another lecture, this time on beam deflections. And this would be chapter 10, by the way, for my students at Northeastern University for the ME 2355 course. Okay, so my objective for this lecture is to show you how you can determine beam deflections or deflection of beams for a given beam, with simple loading. But first, let me, before I explain what I have drawn here, let me talk about different methods that we can use to determine deflections of beams. There are many methods that could be used. Namely, I'll list them here for you. One is the method that I want to talk about right now, is known as the integration method. Another one is the superposition method, which is actually a shortcut, and it requires having tables for different type of beams. One is energy method, and there are more methods, but I'm just putting four major methods here. The other one is using actually the area under the moment diagram to determine the deflection of beams. So this is known as the area moment, which is a graphical approach basically. So the area under the moment diagram is used to determine the deflection of beams. So my objective, at least in this chapter, is to show you how the integration method and eventually the superposition method in another lecture can be used to determine beam deflections. Okay, so let me start by, I have drawn here a simple cantilever beam with just a concentrated load acting at the end. And you see this beam is going to deflect as indicated in the red here. The deflection curve is known as the elastic curve. And imagine if you had the equation of this curve, y, the deflection curve or elastic curve, y as a function of x. Then you can plug in any x value you want and figure out the deflection at any position you want. Of course, what we need is the maximum deflection, which in this case will happen at this right end. Okay, so in the integration method, let me show you how we start, or with what differential equation do we start, so that we can take integration and eventually arrive at the equation of the deflection curve or the elastic curve. Okay, you guys recall that earlier in the chapter when we wanted to calculate the bending stress, we had the flexure formula sigma equal my over I. Also, you guys recall that when we talked, in order to derive this equation actually here, we said, okay, that epsilon, the normal strain, is going to be a function of radius of curvature rho and where you want to calculate that epsilon. So in this case, y would be the distance from the neutral axis to wherever you want to calculate this epsilon. Also remember that Hooke's law, as long as we are within the linear elastic zone, sigma equal E epsilon. So if instead of sigma you put my over I, and instead of epsilon you put y over rho, you see how y and y cancel. So we end up getting 1 over rho equal m over EI. And this basically becomes our differential equation of the elastic curve. Of course, not in this form. I have to add something to it. So if you go back in your notes, actually, you will see this equation in your notes somewhere. Okay, now, you guys also know, probably from dynamics or maybe some other course, physics, that radius of curvature can be determined by using this equation 1 plus y prime squared raised to power 3/2 divided by second derivative of y double prime. So now if we say y prime, which represents actually a slope, remember y prime represents dy dx, which is a slope. Say if the slope of these deflection curves, this elastic curve, is small, we say it equal to almost equal to 0. What will happen then that this term is gone, and then simply rho becomes 1 over y double prime. Therefore, this guy becomes y double prime. And as I said a minute ago, this becomes the differential equation of the elastic curve. And so this is going to be the base for the integration method. So let me show you a very simple problem, how we can do this to find the equation of the elastic curve and determine the maximum deflection. The most trivial or typical problem that we can do is shown right here. If I go back to our cantilever beam and I take this to be my x direction, right? And I say this is L, the length of the beam is L. Remember, the equation is, in a way, EI y double prime, if you rearrange that equation, equal M, or y double prime equal M over EI. All right, so the first thing I want to show you is that if you can find the equation of moment as a function of position for this beam, and that's only one equation, then you are pretty much done. You have to integrate twice to get y. So first of all, we can actually cut the beam and use the right-hand side or the left-hand side to find that internal moment. Let me use the left-hand side. So if I want to find the left-hand side, you know by inspection that the reaction load here would be P, and the moment also developed here would be P times L acting counterclockwise. So now go ahead and cut the beam here, right? And you have a load here, P, and a reaction moment PL here. And remember, this is X where we cut. And now we have an internal shear, which I really don't care about, and an internal moment. Make sure that you show your internal moment in the positive sign convention that we discussed in the class when we were doing shear bending moment diagrams. So now, if you take moment about this point, say point O, where you cut, and use this as positive, then you end up getting M. The moment of P about here is minus Px, and the moment of this moment already exists as moment reaction, that would be PL equals 0. Therefore, M becomes Px minus PL. And by the way, this is the equation of the moment for the entire length of the beam, by the way. So this is valid for the whole length. So we only need one equation for the moment. Okay, so now the next thing we do, we say, okay, EI y double prime equal M. What is M? M is Px minus PL. And you see, from here, everything is simple. So we integrate once, we get EI y prime. So that becomes Px squared over 2 minus PLx plus a constant of integration. I call it C1. So what is this constant of integration? Remember, y prime represents a slope. What can we tell about this beam? Remember in the last page, I showed you that this beam is going to deflect like that. Therefore, its slope must be 0 there. So at x equals 0 rather, sorry, the slope y prime is 0. This is known, by the way, as a boundary condition. So we need boundary condition in order to figure out our constant of integration. So if this is 0 and x is 0, therefore C1 becomes 0. So the equation that represents the slope then, EI y prime rather, sorry, is Px squared over 2 minus PLx, and C1 is 0. So this is the equation of a slope. So now go ahead and integrate one more time. We get EI y equal Px cubed over 6, right? Minus PL over 2x squared plus another constant of integration, C2. And guess what? C2 is also 0 because the boundary condition is at x equals 0, y is 0, right? Right here. There's no deflection. Therefore, C2 becomes 0. So here we go. This is the equation that represents our deflection. EIY equal Px cubed over 6 minus PL over 2 x squared. That's it. Now, of course, you could put the EI here if you want. Right? And now, let's say you want to find your maximum deflection. Maximum deflection happens at x equal L. So go ahead and put x equal L here. So if you do that, what do you get? You get y equal Px cubed over 6 minus PL cubed over 2. Right? And if you calculate this, what do we get? We get 1/6 minus 3/6. So we end up getting minus 2/6. So we get minus PL cubed over 3 EI. I forgot the EI, by the way, here. Sorry. Right? Why negative? Because the deflection is downward. So basically what I'm saying is, so you could write actually your answer like this: y max equal PL cube over 3 EI downward, like that. Okay? So this would be the deflection right here. Now you can plug in any number you want if you know what the material property of the beam is, what the moment of inertia of the beam is based on the cross-sectional area, cross-section of the beam, and the length of the beam and the applied load. Then you can calculate the deflection. You could also use the equation of slope and figure out what the slope is. The slope would be actually the tangent to this, which we usually denoted by angle theta, the slope at x equal L. What I will do in the next lecture, actually, which hopefully would be around 10 minutes, I can show you that actually you can cut this beam and use the other side. Of course, the equation would be different, but the outcome is going to be the same because you're changing your reference, and this would be your x in that case. Okay, please leave any comments if you have, or send me an email, or let me know if you have any questions. Thanks for watching and listening. I'll come back pretty soon with another lecture.